In this last week, I'm here in an optics lab at the UK Astronomy Technology Centre to talk about spectroscopy. So what is spectroscopy? Well, light, any natural light source is made up of light of a mixture of different wavelengths. So red light has a longer wavelength than blue light. Infrared has an even longer wavelength. Radio waves have an even longer wavelength. Likewise, ultraviolet has an even shorter wavelength than blue light, and X-rays are just waves with a very, very short wavelength. So the art of spectroscopy is the technique of splitting light up into its component parts so we can tell how much there is of different types. Now, if I was to draw a graph of the intensity of light plotted against the wavelength of the different components, that shape would be the spectrum of the light, and we'll see some examples in a moment. So later on we'll see how we actually do that, how we split the light up and measure it. But first of all, I wanted to show you how there are three powerful things we can do with a spectrum. So trick number one is that we can use the spectrum to measure the temperature of an astronomical object. Now this works because hotter objects emit bluer light. Now we can get a rough idea of the colour by using filters, as we discussed in week 2, but we get a much more accurate picture if we can actually get the spectrum. So this illustration I'm showing you here shows how the spectral shape of the light from a star changes as we change the temperature of the star. We can get a pretty accurate measure of the temperature of the star. So then once we have the temperature of a range of stars and we have their luminosities as well, as we saw earlier in the course, if we plot luminosity against temperature, it falls into a pattern. That's the famous Hertzsprung-Russell diagram that Catherine showed you, and it was the secret to understanding how stars work. So the second trick is that we can use spectra to tell what objects are made of. So how does that work? When we look at the spectrum of a star like the Sun, as well as the smooth range of light, you can see here in this image, you also see dark features at very particular wavelengths. Now those dark features are caused by atoms in the atmosphere of the Sun absorbing light at very specific wavelengths. Now this happens because of the way atoms behave. So quantum mechanics tells us that atoms can exist in a discrete set of energy levels, and if light is approaching of exactly the right wavelength, it can kick an atom up from one energy level to another. It has to be just the right wavelength to do that trick with a specific atom. But then once that light has done that and kicked the atom up to an excited level, then that light has been absorbed by the atom, and so it's missing in the light that we see, and so we see a dark feature. Now, those sets of energy levels for an atom are unique to different kinds of atoms, to different elements. So likewise, the missing lines that we see that correspond to those atomic energy levels are fingerprint for that atom. So we can tell what atoms are present by seeing which wavelengths are missing in the spectrum. So that's how we can tell what a substance is made of, by those missing lines. That's how it works in a star, that the atoms in the atmosphere are absorbing the bright light from the star. If we have a glowing gas cloud, as we see for example in the Orion Nebula, it can glow at discrete wavelengths which are exactly the same. And again, it's atoms which are already excited and are dropping back down. And that makes emission lines rather than absorption lines at the same wavelengths. Now, molecules as well as single atoms can do a very similar trick. They likewise have a unique set of energy levels and so produce a spectrum with discrete lines. But in the case of molecules, those lines come out in the far infrared and in the radio region, so we typically measure them with radio telescopes. So this image I'm showing you here, this shows the far infrared spectrum of the Orion Nebula as measured by the Herschel Space Observatory. And the spectrum is superimposed on an image of the nebula. And you can see it's just chock full of lines that correspond to quite complex molecules. And if it wasn't for this technique, we would have had no idea that those complex molecules existed in space. The third trick is that we can use spectra to measure the velocities of objects. Now this is the trick that we're going to concentrate on for Catherine's science sections this week. So let's see how that works. Now sometimes when we get the spectrum of an object and we look at those dark lines or the bright emission lines, sometimes they appear at the wrong wavelength. When that happens, it's because of the motion of the object. As you heard from Catherine in weeks 3 and 4, the Doppler shift is an effect that means when an object is moving towards you or away from you, the light gets squashed up or stretched out. Now, if we measure the amount of shift, then we can tell the velocity of the object. And we can use that in all sorts of fascinating ways. So here's an interesting example. This is a picture of the galaxy M87. It's a Hubble Space Telescope picture. And the two little circles you can see either side of the middle are places where the Hubble Space Telescope collected the light to take a spectrum. Now the line plot that you're looking at here shows a small portion of the spectrum from each of those two spots. It shows an emission line from hydrogen atoms. Now you see that on one side of the nucleus of the galaxy the line is shifted to the blue, and on the other side of the galaxy it's shifted to the red. And that's because one side of the galaxy is moving towards us and the other side away from us. That tells us that in fact what we're looking at in this galaxy is a disk of gas that's rotating. So from the size of that shift that you see in that plot, we get the delta lambda, and we can work out the velocity. So we know the rotation speed is about 550 kilometers a second of that gas disk in that galaxy. Then we can play the same trick that Catherine showed you earlier with Cygnus X1. By applying Newton's laws, we know how big a mass must be causing that rotation in the center to make that particular speed. So we can work out the mass of the object in the center, and it comes out in this case to be about 3 billion solar masses. Now that's where it gets weird, because when you look at the starlight in the center, then the number of stars in the middle is 1,000 times less than that. So whatever this mass is that's causing the gas to rotate is dark. So we indeed think it is a supermassive black hole, and that's how we know it's there. So that's our 3 tricks, and now Catherine is going to tell you a little bit more about how we use this velocity trick to study the acceleration of the universe and dark energy.